All right, introducing vectors. Before we start on what exactly a vector is, we'll start as thinking about some oversimplifications. A lot of times when people think of vectors, they just think of them as arrows, and all we're going to do is just play around and do math with arrows. The more correct way to look at it is a vector is a quantity that's something that's measured, and it has a direction as well. So, for example, the force of gravity is a force that not only has a pull to it, the force of gravity itself, but it has a direction. It pulls you towards the center of the Earth, or downward from our sense. So when we think about vectors, we need to think about three things. The first thing is the magnitude of the vector. That's the size or the quantity or the force that's going on. That corresponds to the actual length of the vector. We call that magnitude. We also have the concept of direction. So that would be sort of relatively the angle at which the arrow or the vector is pointed. And then we have the concept of sense, which is the more precise idea of direction. And when we talk about sense here, here's point A and here's point B, and we see the arrow headed off in the right direction. So AB is the vector that's shown here. Sense, if we change the sense, we would be talking about vector BA. So we're going in the opposite direction in the same angle. So those are the three things we need to think about when working with vectors and just understanding what they are. There's a force or a magnitude, which corresponds to the length of the vector, and there's a direction, which corresponds to the angle at which the vector is slanted, and then there's the sense, which will tell you where along the vector you're going, well, top to bottom or bottom to top, and that's using the letters we can determine that, or the arrows itself. So in your packet, you should see this this slide. Make sure that you understand the different notations, variant notations. When we talk about magnitude, we sometimes use double bars, but more commonly now it's like using the absolute value bars. So the magnitude of vector OA, or just OA, corresponds to the same meaning, or the magnitude of bold-faced letter A, and these are modified notations. So we need to make sure that we understand a couple things. Vector notation is different from country to country, but generally speaking, you should be able to understand what you're talking about. In IB, you'll see a lot of these notations used interchangeably, so just be aware there's different ways to express different things. We have this next concept is this thing called vector equality. When are vectors equal to each other? And essentially, if vectors have the same magnitude, direction, that is, they don't intersect, and they have the same sense, that's important, then those vectors are considered to be equal. For example, here we see two vectors AB and A1, B1. They are in the same direction, and they have the same sense, and they have the same magnitude, and therefore it is safe to say that even though these are in different places in space, they are in fact equal vectors. And contrast that with these two vectors, A, B, and A1, B1. What you see I've done is I've changed the sense of the second vector, and therefore these are not equal vectors. What we can do, though, is we can use the negative sign to change the sense of the vector. And so when I look at this vector AB and I see A1, B1, I could just take the opposite of B1, A1 vector, and that would make these, in fact, equal to each other. So we can say which of these statements are true, and we've got the figure A, B, C, D. It looks like a parallelogram, and the first question is DA equal vector to BC? So here's DA, and here's BC, and we can see that they are parallel. They have the same magnitude. However, they do not have the same sense. Therefore, these are not equal. If I say AD and the opposite of DC, so here's AD, and here's DC. The opposite of DC goes this way. Clearly, they're not equal vectors in any stretch of the imagination. AD and CB. So here's AD and here's CB. Once again, they're opposite sense, therefore they are not equal vectors. And finally, DA and the opposite of CB. Here's DA and here's the opposite of CB, which would be BC. And again, not equal. So none of these statements are true. So we have to make sure we're paying attention to that as we work with our vectors. So what are some things that we do with vectors? We can actually Extend the length of a vector by multiplying it by a scalar. To understand that, it's a very simple idea. Here's a vector AB, and if we take that vector and add it to itself, basically doubling it, then we get a new vector that is twice the size. So looking at the figure here, A3, B3 is the result of 2 times vector AB. Once again, here's vector AB, and we double its length, and we get the whole new vector shown. We could also use negative numbers as scalars, and what that's going to do, of course, is change the direction or the sense of the vector in addition to its magnitude. So I'm going to double the magnitude, but I'm also going to reverse the sense. That didn't work. I think you understand my meaning. I hope you do. Anyway, that scalar is pretty straightforward. The next video, we're going to look at vector addition and vector subtraction, and we'll get into some more interesting and engaging high-level problem solving. But I did feel it necessary to at least point out some of these fundamentals. These fundamentals are things that are going to become clear and obvious as you do your work, but if you don't keep these kinds of fundamental principles in mind, for example, the notation, the definition of magnitude, the difference between direction and sense, and how to make sense out of sense. If you don't keep all that stuff straight in your head, then the more complicated work is going to be way too difficult to comprehend. But if you keep these basics in mind, then we should be able to move along quite well. So the next video, addition.